Hi everyone, my name is Sebastian Hubenschmid. I'm from the University of Constance, and in this video I'll present our paper Around the Smartphone, where we investigate the effects of virtually extended display size on spatial memory. This work was made possible thanks to my co-authors Johannes Zagermann, Leicht, Harald Reiterer and Tiare Feuchtner. So with our work, we wanted to take a closer look at the screen sizes of different smartphones. Because on the one hand, smartphones give us access to these vast information landscapes, but at the same time, we can't really make them any bigger than they are now, at least not without sacrificing device ergonomics and portability. One promising possibility in this case is the use of augmented reality glasses to extend the screen of a smartphone with a virtual display. With such hybrid use interfaces, we can benefit from both the familiar touch interface of a smartphone and also the large output space from augmented reality. And prior work in this area has already shown some really compelling use cases for these virtually extended screen-aligned displays, but there are still some open questions. For example, are there any negative impacts from switching our visual attention between what are basically two different output spaces? Or are there any effects because the input and output space have different sizes? And even if we have access to this unlimited screen space through AR, is there actually any benefit from increasing the screen size? So to answer this, we looked at related work in the field of spatial memory, which is the part of our memory that helps us encode our spatial surroundings. Spatial memory has been studied quite well in the field of HCI, so for example in terms of display size, input modality, visual landmarks, interface layout, virtual field of view, and so on. But here one consistent finding across multiple studies is that seeing more information can improve spatial memory. For example, a study by Reiterer and colleagues compared different peephole sizes for map navigation. And their results showed that spatial memory improved with bigger peepholes, but they also found that there are diminishing returns on the benefits beyond the size of a tablet. So the question we wanted to answer with our study is, can we apply these prior findings to the use case of virtually extended smartphone screens? And to this end, we conducted a controlled lab experiment using a well-established task from prior work, which consists of a navigation phase and an object location recall phase. And during the navigation phase, participants were equipped with an AR headset and a smartphone. With this setup, they had to search for a symbol on a large 2D grid map by using touch gestures similar to what you can find in a map navigation app. Overall, the grid map contained several target symbols and also distraction symbols, while the participant's current target was shown in the middle of the smartphone screen. Participants completed this task by navigating to the target symbol and placing it roughly in the middle of the smartphone. The map then jumped back to its starting position and participants had to search for the next symbol. Once they found all the symbols, participants then took off the AR headset and moved to a desktop monitor with an empty grid map for the object location recall phase. And here we asked participants to place the target icons from the previous phase on an empty grid map. We used mouse input for this to remove possible influences from motoric memory and to stay comparable with prior work on spatial memory. And this task allowed us to compare 4 different conditions during the navigation phase, which you can see here. So first we added a baseline condition without any kind of virtual display extension. And here participants still wore an AR headset for better comparability. For the other conditions, we extended the smartphone's display using the AR headset to 3 commonly found display sizes. So here we used a tablet-sized extension, a desktop monitor-sized extension, and a television-sized extension. And each condition had a different grid map with a unique item set to avoid learning effects. We also used a separate map for the training task with letters of the alphabet instead of symbols. For our experiment, we recruited 24 participants from our university. And the participants were mostly students from different disciplines and between 21 and 36 years old. And while many were familiar with the use of smartphones, their experience with AR was rather mixed. And we used a within-subject design and fully counterbalanced the different screen extension sizes to further avoid learning effects. And our experiment started with a general introduction of our study and a demographic questionnaire, followed with a short training phase to get participants comfortable with our system. The participants then had to search for 6 different icons for the navigation phase, which was repeated 4 times, which then was followed by the object location recall phase. Each condition was wrapped up with a raw NACTLX and user experience questionnaire, and each session was concluded with a semi-structured interview to gain qualitative insights. So we organized our findings based on 3 research questions. So firstly, we looked at the effect on spatial memory. So how does the virtually extended screen size affect users' navigation behavior and performance? We measured this in terms of navigation path and speed, task completion time of the navigation phase, and accuracy in the object location recall phase. Secondly, we looked at the workload. So does a virtual screen extension cause an increased workload in terms of cognitive load or ergonomics, since the users basically had to switch between the smartphone display and the virtual AR display. And here we analyzed pupil size, the eye gaze and head movement, and also complemented this with a NASA-TLX questionnaire. And lastly, we also looked at how the user experience is influenced by virtual screen size. This was analyzed with the user experience questionnaire, as well as qualitative data from our concluding interview, including a subjective ranking of our conditions. So for this video, I'll briefly summarize the key findings of our experiment, but you can find more details in our paper. Our first main finding was that all of our virtually extended screen sizes were beneficial for user experience and task completion time for the navigation phase, which is in line with findings from prior work. And while the effects for the tablet-sized extension were at times not statistically significant, for example for task completion time and attractiveness in the user experience questionnaire, we can also see here that the impacts of the desktop monitor and television-sized extension were statistically significant on all scales. So especially the desktop monitor-sized extension was a sweet spot in terms of spatial memory, workload, and user experience, which is also in line with prior work. And in this regard, further research is also necessary whether the actual sweet spot depends on the user's day-to-day experiences. But unlike prior work, our results show that going beyond the desktop monitor size was actually detrimental again, at least for spatial memory and ergonomics. So in our figures, you can see that, for example, the improvements for recall accuracy during the object location recall phase were statistically significant between our baseline and the desktop monitor-sized extension, but not for the television-sized extension. And similar results can also be seen in the NASA-TLX questionnaire, for example, with regard to the physical demand and performance. So here we see a statistically significant improvement between the baseline and the desktop monitor-sized extension, but not the television-sized extension, which also resulted in a slightly worse overall score for the television-sized extension compared to the desktop monitor size. To our surprise, the tablet-sized extension also performed slightly worse in terms of spatial memory and workload. So for example, the participants' gaze movement increased significantly once we introduced any kind of virtual extension, but there was no statistically significant difference in between these virtual extensions. However, when looking at the path length during the navigation phase, we didn't see any kind of improvement when comparing the baseline with the tablet-sized extension. And on average, participants actually performed a little worse with the tablet-sized extension. So we think this might be because the smartphone provides a kind of reference frame and therefore a physical affordance to the user, which is disrupted once we add the basically unknown affordance with the virtual extension. But more research in this regard is necessary to find the actual underlying cause for this. If you're interested in more details or want to know more about our prototype, please have a look at our paper or browse through our open source project on GitHub. Thanks for listening.